So let's get started with this. Pressure controls, pressure control valves. Okay, we use valves to control pressure in our system in order for our system to operate as designed. Now, we're going to limit maximum pressure in a system or limit maximum pressure in a component of a system by using these different types of valves. So I've got here limit maximum system pressure or regulate reduced pressure. Okay, it's another way of thinking about maximum limiting pressure is to operate at a reduced pressure in some parts of a circuit, or if some materials are in use in our circuit, certain portions of the circuit. And other functions wherein their actuation is a result of a change in pressure. Okay, so I want to clamp something, and then I may want to press onto that item. And the example I'm going to give is survey stakes. So in Canada, when you do a survey stake for a pipeline, there's got to be certain information on it, and it's got to be found, it's got to be readable. So often what we do here in Alberta with gas pipelines and things like that is a stake, a piece of metal comes through a press, and then it will be clamped down in place, and then we'll have a machine that punches the information into it or presses the information into the metal. And then we will bring that press back up, we'll cut the stake, and then we'll release the clamp that may be holding the steel, run the motors to extend the next piece of steel. So I've got a sequence of operations here that may be operating at different pressures. I may want to clamp the metal or cut the metal with different pressures depending on which metal it is, if I'm using a stainless steel or just plain old galvanized steel. So we're going to set the different pressure controls in our system. So what we've got here, the operation is based on a balance. Okay, it's a balanced system between the pressure derived from a spring and the pressure in the valve, okay, from the fluid acting on an area. So most of our valves have a small spool or a poppet acting against a spring. And that poppet has a surface area. The pressure of the fluid acting on that surface area of that poppet is acting against the spring from the other end to determine if the valve should open or close or modulate or some position in between. So most of these valves technically have an infinite position, but we tend to draw them in their default closed position, and we draw them as either open or closed. And a lot of the time we think of our circuits as opening and closing quickly or being in some partial position. The reality is they have an infinite position between open and closed, and most of them are going to sit in one of those extreme positions for our circuit while it's operating, or modulating in between those. So they are infinite, but we're not going to draw them as infinite, and we generally don't analyze them as infinite because we generally analyze our circuits in static conditions, not in a dynamic condition. So this valve can assume any position between fully enclosed, fully open and closed, but we're going to analyze usually one or the other, and that is dependent on the flow rate and any pressure differential within our system. Now we can control lots of different things. Now there's a list here of some valves: a relief valve, a sequence valve, a brake valve. The list is quite long. Now, one thing in hydraulics that we do is we name the valve for its action. What is it doing in our circuit? The result is I have a valve, an off-the-shelf valve, okay, and if I'm using it in a particular function, I'm going to use it as a different name. So I can call something that may be used to unload a circuit. We're going to cover unloading valves. I might use the exact same valve in the exact same condition to operate the brake on a rotating motor. I'm going to call it a brake valve, even though it's exactly the same valve. So don't be surprised when you see a symbol and a name associated with it, and it's got a different name than you've seen before. Remember, this whole system wasn't really designed by engineers. It was designed by mechanics and millwrights, and the naming convention is just basically on what we're using that valve for. Okay, so a relief valve, we're going to relieve the pressure in the system. A sequence valve, we're going to operate valves in a certain sequence. I'm going to call it a sequence valve. I am braking a rotary motor. I'm going to call it a brake valve. Okay, so the naming doesn't give you any hint to how it actually functions. Okay, its name is based on the purpose that we're using it. Okay, and some valves you can use 2 or 3 different valves as a brake valve, absolutely. But depending on the pressure and how much control I want, I may choose a different valve to use. The drawing still just calls it a brake valve. I've got to look at the schematic a little bit more and maybe the parts list to understand exactly what we've got there. Now, all our valves are going to be classified based on certain numbers of things. What's the maximum pressure it can handle? What's the flow rate that can move through the valve? What's the operating pressure that we're going to operate? Do I have a screw-on fitting, or is it a different type of fitting that we have on the valve? So there's a large list of things. Even when I know which sort of valve I want to use, I have to start thinking, what sort of valve is it? Is it a cartridge valve? Is it a stack valve? What is it? There's a large number of things we talk about when we start classifying our valves. We're not really going to talk about most of those things in detail to this latter half of the course. At this stage, we just want to be able to understand the function of the valve and how it works. So a relief valve, we've all used those in labs 2, 3. We will use a relief valve every week. They are found in every hydraulic system. They are a safety device. They are setting the maximum pressure that we will see in our circuit. If for some reason something happens to exceed that pressure, the valve will open, allowing the fluid to be bypassed from the circuit, discharged straight back to the reservoir, setting at a maximum pressure. Okay, so it's a safety device. You've got to have them. It's like having a fuse in an electronic circuit. It sets the absolute maximum. The fuse sets the maximum current in the circuit. It will fail if we exceed that current. Poof, it's turned off. You got to go and replace it. The beauty of something like a relief valve is it doesn't fail. It just diverts fluid away from the circuit, okay, until the requirement for the high pressure disappears. So it's automatic. It's like having an electronically resettable fuse, which we do have on circuit boards and things like that nowadays. We can get electronically resettable fuses instead of your old-fashioned fuse that just blows and needs replacing, like we saw in the multimeters in our MEC 205 labs. So that's why it's excuse me, this initial statement, they are found in every system. They are a safety device. They are normally closed. And we want to put one of them, often our circuits have more than one, right after the pump. Okay, so we want to protect as much of the system as possible from overpressurization. So let's do that flow diversion from where the flow is created in order to set that maximum pressure in the system. And just if the pressure increases, the valve opens, the fluid is dumped back to the reservoir, maximum pressure is maintained until the pressure required in the system drops. Okay, so it's set to a preset condition, and it just runs. Now the symbols we've got here, we've got this direct acting pressure relief valve, which is actually not 100% correct. As I spoke to you in the lab in the first week about, there's a dotted line over here where I've got my arrow and cursor going with a bit of leakage going through it. Okay, this symbol here is the generic symbol we'll use for pressure relief valve. Generally, even if we're using the pilot operated pressure relief valve here, and we do this a lot in hydraulics, we use the simple basic version. Even if it's a pilot operated valve, we tend not to put it in our schematics, except at a teaching level here, like we're doing at SAIT. So direct acting pressure relief valve, pilot operated. We're going to get into more detail over why I would choose one over the other during today's class here. Now let's look at this direct acting pressure relief valve. So I've got a very old drawing here because the older valves have a structure that we can follow very easily. We can see how they work compared to a modern spool valve that will have kind of complicated things going on there. We don't want to cover the complicated stuff. We want to keep it simple to get the basic understanding of how this works. So this drawing has a cutaway of a basic direct acting pressure relief valve. We can see there's a spring here inside here that is operating against what we call a poppet in this case. And this poppet is pushed up against what we call the seat, okay? And then exposed to high pressure or the pressure of the system. The other side of the spring, okay, we can see there's a handle there that when we can adjust it. Now, some systems we'll take the handle off, and some systems we won't even have a handle on there. We'll have a preset maximum condition. And once again, this is for safety. I don't want someone necessarily adjusting something. So often in an automated system, especially, I have one of these hidden away somewhere to set to a maximum pressure. So it doesn't matter what the operator does or what the programmer does to set a pressure setting. I'll have one of these hidden in the background that is my safety device's absolute maximum, say 3000 PSI. It doesn't even have a handle on it. Okay, I don't want someone turning it up and causing a failure in my system. So it's very common to have these all over the system, and some of them are not adjustable or hidden from adjustment. So what happens here, we've got a very heavy spring. It's going to work a lifetime. It is a safety device. So this is going to be better than the springs generally found in most of our valves because it's going to set that maximum pressure as a safety device in the system. So I've got here a circuit, a basic circuit to extend a load. And in this current position, the DCV, the directional control valve, is set to allow the fluid to go through and cause the cylinder to extend. And there's 8,000 pounds of force required to make this extend. 8,000 pounds, okay, F equals PA, pressure, okay, and area are going to make up this force. I've got 10 square inches, therefore my pressure must be 800 PSI. So I've got 800 PSI in the system in order to extend this load. When the load is fully extended, of course, the force can continue to rise because the opposing force is the end of the cylinder. Virtually infinite, okay, way more than we want to see in our system. So the pressure would start to rise. So what would happen is, as that pressure would be rising, it would be acting against this spring, this pressure over the area of this poppet that's exposed, acting against the spring until it reaches a certain pressure where it would start to crack open. We'll go into more detail on some of the terminology. It would start to crack open and allow fluid to escape. Okay, and this would be considered fully open at my 1000 PSI, because at fully open, it allows all the fluid to go through. So when the cylinder extends, absolutely fine, requires 800 PSI of force. When it's fully extended, there's nowhere for it to go anymore. The pressure would go up, rising to 1000 PSI, because that's the setting that we have at our valve. Okay, basic operation of this valve. Do nothing until the pressure rises too high. If the pressure rises too high, open up, relieve the flow so that the pressure does not get any higher. Now, of course, if you under-design this valve, say this valve is only designed for 1 gallon per minute, and I had a 3 gallon of minute flow, okay, what's going to happen? Well, the pressure is going to continue to rise. The pressure will rise above the setting because this is going to be fully open at 1000 PSI. If I try to get more flow, okay, well, I'm only actually going to get the 1 gallon because there's nowhere else for it to go. The pump will work harder, and I've got more resistance to flow because I've got resistance from the valve size, not just the valve setting, and the pressure would actually exceed 1000 PSI. So it's important to make sure we've got valves designed for the maximum flow in our circuit. So direct acting pressure relief valve. I've spoken about this on the previous slide. We've got a limited flow based on this, how far this can open this poppet, push the poppet out of the way and allow a certain volume of fluid to flow through. We've got a spring force being delivered. The negative is this is very inefficient, because what's going to happen is it doesn't just go fully open at the 1000 PSI. it cracks open a little bit as the pressure starts to rise, okay? And generally in this configuration, maybe about 700 PSI, this would actually crack open and start thieving flow away from my system. Remember, this design, the previous circuit was operating at 800 PSI. So at 700 PSI, if this opens and steals a little bit of fluid, okay, the system's operating at 800 PSI. I'm dumping a little bit of fluid because this is opened at 7. That's some fluid not available to do work for me. That is fluid I've generated at high pressure. So it is taking away fluid that I've paid a lot of money to generate at pressure and flow. So that's why I use the word thieving. It's taking away cost. It's always increasing my cost of operating. It's also, because it's taking away fluid, is going to slow down the movement of that piston. So we have to think about this in our design. And this is why this is not a particularly good design to operate at above maybe 2/3 of the setting of this valve, because it's going to allow a bit of leakage through this valve. We're going to thieve a bit of flow. Okay, so it's inefficient. And the word here at the bottom is called override. The override is the distance between, or the change between the cracking pressure when it cracks open and when it's fully open. That term is called override. Okay, so we adjust it by adjusting a screw. Okay, as we compress a spring, as we adjust it in, it's going to take more force and more force to continue compressing it. So if I can compress it at one end with the spring, it's going to take more force from the fluid acting across that area to compress and open that valve. So it's a very simple system to set. Okay, so that spring force, that maximum spring force, is going to set parameters that we're going to operate under. Nothing else new on that slide. I think we've talked about everything. So important things to note: the cracking pressure. Okay, so here I've got a excuse me, my valve set to 1000 PSI. In reality, it's going to crack. Maybe there's 600 to 700, 750 PSI, depending how old it is, how good that spring is. It's going to crack open, and a little bit of fluid is going to start going through. As the pressure on the system continues to increase, pressure over this area of this poppet, more and more force because of increased pressure, pushing against this poppet, opening it further, allowing more and more fluid to flow until finally I reach the maximum setting that I've set this to, in which it would be fully open, allowing all the fluid flow through the valve. So when we set these things, we need to have created a system where pressure is high to be able to set the maximum, and where the maximum flow exists. I've got to look at both the flow and the pressure in the system being maximized in order to set this valve. And that's why in the labs, we deadheaded, we call it deadheading the cylinder. We moved it to its full extension of travel, and it couldn't move anymore. The pump's still running at 1 gallon per minute. Pressure builds up because there's nowhere else for the fluid to go. And that's the point that we set the fully open pressure for these DCVs. Full flow pressure, I talked about that. Pressure override, the difference between the cracking pressure and the fully overriding pressure. Now this, as I said, is a problem if I'm operating up near the peak of this setting, because it's costing me money. I am spending money generating flow at pressure and diverting it straight to tank when it should be doing some work for me. So not the most efficient thing we want. So what we do instead is we can use a pilot operated pressure relief valve. And that's why we tend to use it sometimes in the lab in order to be able to get better performance, okay, and save money. In industry, we use pilot operated pressure relief valves as the standard, not the direct acting pressure relief valve. But first, I'm just going to play a video on direct acting relief valves. Now, this video is from a company called Lunchbox Lessons. They are one of the few hydraulics learning sites out there that I have never found an error in. So they are very good. They've got lots and lots of videos. The guys who built this tend to be in the mobile hydraulics. So if you go on the website, you're going to see lots of videos that we don't really cover because it's mobile hydraulics. It's very good. In fact, it's a guy in Red Deer we discovered a couple of years after we started using this. I think he came around about 2016. I think he started working in 2015, creating these videos. Very good, accurate videos if you want to go and learn more about hydraulics. But let's just play this rather long video about direct acting pressure relief valve. I might stop it early.
Welcome to Lunchbox Sessions, bite-sized industrial training.
Hello, this is Carl from LunchboxSessions.com. In this video, we will examine the function and performance of a direct acting relief valve. This is a simple type of pressure valve that has only one spring and one poppet. Currently, the relief valve is set to 800 psi. We know this is the setting as indicated on the gauge because all of the pump's flow is being diverted to tank through the relief valve. Watch the system pressure on the gauge as the spring setting of the relief valve is reduced. The system pressure falls as the setting is reduced. As long as 100% of the pump's flow is passing only through the relief valve, then the reading on the gauge indicates the current relief valve adjustment. Let's increase the adjustment of the relief valve to 1000 psi. Now let's remove the bricks from our brake shoe brick stacker on the hydraulic motor cymbal. The brake shoe brick stacker allows us to induce system pressure in an easy-to-understand way. As we gradually start to add bricks to the stacker, we notice the system pressure is rising on the left side of the graph. Remember, we have adjusted this relief valve to 1000 psi. As we continue to add bricks to bring the system pressure to just above 500 psi, we notice the graph shows that there is now flow passing through the relief valve. The relief valve is said to have cracked open. In this case, the word crack does not refer to a failure mode. As indicated on the horizontal axis, approximately 1 gallon per minute out of the 20 that are produced by the pump is now being diverted back to tank. Adding more bricks to bring our system pressure to approximately 750 psi, we now notice the motor is turning at only half speed. This is because half of our pump's total flow is now passing through the relief valve to tank. But since the hydraulic motor is still turning, we have not yet found nor reached the relief valve setting. As stated earlier, the relief valve setting pressure is the pressure at which 100% of the pump's flow passes only through the relief valve. Now that we have stacked enough bricks to stall the motor, we have reached 1000 psi, which is the current setting of the relief valve. What we observe in this model is that the relief valve, with only one poppet and one spring, has a very large pressure override. Override is the difference between cracking pressure and the true relief valve setting. In this particular design, the pressure override value is 500 psi. The relief valve starts to divert system flow, making the motor slower at 500 psi system pressure, continuing to increase diverted flow all the way up until 1000 psi is reached.
Okay, let's stop that there and move on to the next detailed explanation covering or graphical showing what we were just talking about, the operation of that valve. So, what is a pilot operated? Remember, pilot means steer. Okay. So, in a pilot operated valve of any type, we have more than one valve. We have an extra valve to steer the main valve. Okay. So, we have a valve that is, going to be in charge, but it's not doing most of the work. Okay. And that's generally what the pilot stage of a valve is. This gives it massive operating efficiency. Okay, so we've got here a pilot stage contains a small direct acting relief valve allowing minimal flow, which controls the pressure on the top of the balance piston. What does that mean? If I look at this cross section, this pilot stage here is just like my plain old pressure relief valve, my direct acting pressure relief valve. It's the one going to be taking most of the pressure, but it's not the one going to be taking most of the flow. This other one valve here is going to be dealing with most of the flow. So what happens here?
Hey, Chris. Sorry to interrupt. Yeah.
Yep.
Your voice was kind of quiet there.
Yeah,
Not better.
sorry, I had the mic in the wrong place because I've been drinking coffee. Sorry, I'll start again. Pilot operated pressure relief valve. Now, when we have a pilot operated, that pilot part is usually just another valve. Okay, it's in this case a direct acting valve, and most of our pilots are effectively a direct acting relief valve. This is going to deal with the majority of the pressure. This is where my super strong spring is that has to accommodate several thousand psi, okay, or the force several thousand pounds against it. And it's only going to accommodate really the pressure, and a small bit of flow is going to go through there. Its purpose is to cause the main part of the valve to act, to open and close, letting the main volume of the fluid go through. But we want to do this with a very, very small spring. We only want to lose a little bit of pressure here. We want it to crack. Ideal valve would crack at the pressure would be fully open. That's not realistic. It's not going to crack open 1,000 psi and go fully open. That's going to be a very expensive valve to design. It's going to have a lot of inconsistencies. So if we can minimize that pressure override, the distance between cracking and being fully open, excellent. And that's what this does. Okay, so what's going to happen here, because this spring here that's listed as 20 psi, my pressure override is only going to be 20 psi. What's going to happen is, as I'm going to talk about this and then in a little bit of detail and then skip through the next slides, which cover this in more detail. Okay, but I've got this pressure going through a valve. Our valves are not set up with this output. We have to put them and tee them into our circuits. But a lot of valves are going to have this direct flow through it, going to the circuit. Now, the red areas are all at high pressure. Okay, this valve is drawn in its closed position. It's normally closed position, as per the symbol in the top right. The blue areas are low pressure, okay, or nominal pressure, 0 psi, a few psi, whatever the filter is, it's dirty or something else in the system. You know, maybe up to 65 psi, but it's nominal. It's nothing compared to 2,000 or 3,000 psi. So these red areas is actually all connected, these two, okay, and then I've got this spool here, okay, this round spool that can move up and down, acting against this 20 psi spring. If you look, there's this tiny little orifice drawn in there that allows a very small amount of fluid through, like a cubic inch per second. Not a lot of fluid when I'm pumping gallons per minute. So it's a small fraction of fluid can escape through that into this area. So this is why at the moment when this valve is closed, it's pressurized because there's no fluid flow. It's virtually incompressible. If I put high pressure at one area, according to Pascal, I've got equal pressure throughout that fluid if it's contained, and the fluid here is contained. So this pressure up here is fairly high. There's a wider channel up here going back to the poppet and acting against this valve. Okay. So what happens as the pressure starts to increase? Okay, so I've got a pilot stage, and let's say it's to 1,000 psi, just to make it the same as what we were talking about earlier. It's set to 1,000 psi, and what will happen is I've adjusted this to 1,000. I've got no idea what's happening internally. I just know I've got it set to 1,000 psi. So what's really going to happen is this spring is now set to open at 980 psi. From outside, it just looks like it's 1,000, but it's actually going to crack at about 980. So when it cracks, it allows a little bit of fluid to move past this poppet. A little bit of fluid. But the fluid moving past this poppet is more than the fluid that can move through this orifice. So I've let a bunch of fluid go quicker than I can let the fluid go in, and the fluid's virtually incompressible. So what happens is that the pressure up on this top side of the chamber drops, okay? Once it's dropped by 20 psi, the spring plus this pressure of say 980 or less psi is going to be less than the pressure acting below on this big surface area, okay? Because the pressure on this surface area is smaller than the pressure on the larger surface area by at least 20 psi, which is the spring, this main valve moves up, opening the flow to leave. This is why the pressure between cracking and being fully open is only this 20 psi. So that means instead of thieving at 700 psi, okay, it's not going to fully open until 980. I could operate that 800 psi load on the second slide, the third slide, without having any fluid loss. All the fluid I'm creating flow for at pressure is doing work for me while we're extending that cylinder. So I'm going to get the full value for my money of generating fluid flow at pressure, and I'm going to get the full speed of my design system. Okay, this is why this pilot stage makes such a big difference. Okay, I've built in this new plunger system that operates with a very low differential in my system. So let's have a look at the next few slides. What are we going to be showing here? Okay, looking at the symbol. There's a small error here in the symbol. Now, this valve isn't the same as this symbol. This valve allows the flow right the way through. So imagine that there's another line here from pressure to system, okay, on the left-hand side. Now, a valve without this right-hand opening would be this symbol on the right. I've got fluid coming in, okay, so fluid coming into the valve. I'm going to bleed off a little bit of that fluid through a very narrow orifice. That's the symbol here, okay? Now on a needle valve, we indicate an adjustment, that we can adjust that needle valve. But here I've just got an orifice, it's not adjustable. That's what this is through here. And it's going to go up, and we see this X on the left. That's this closed port. This closed port is going to allow for remote operation if I wanted it. But in this case, there's just a nut screwed in there to keep it closed. That's what the X indicates on the symbol. If I was using it, I'd get rid of that X and take this line elsewhere. This line, you notice, is the long dash line, okay? Long dash line indicating full pressure, but very little volume flow of fluid, okay? So then it carries on, it's going to act against the poppet, okay? The pressure is going to act against the poppet, okay? So if I think of this arrow as being the poppet and this upstream pressure acting against it, and behind that poppet, I have a spring which has an adjustment handle. That's what we have in the symbol. The fluid, if it pushes through here, causing this to crack open and flow, actually wouldn't be this solid line here. I made a mistake there and I haven't fixed it this year. That would be, once again, a drain line, because now the fluid is no longer under pressure and it's a very small volume. It would actually be a small dash, short dash line correctly from here to this point. When it opens, okay, I'm going to detect this pressure drop. As a result, detect this pressure drop, therefore acting on this surface here, allowing the valve, the spool, think of this arrow as the spool, to move upwards, because the pressure on the other side of the surface exceeds the pressure on the top side of the surface, allowing the full flow of fluid to go through to the reservoir. Okay, so everything in this picture has meaning. Okay, and that's why I like these old valves that, you know, we don't use these anymore. Generally, they're not as efficient as other designs, but it shows you exactly what's going on in the valve. These old symbols were designed with the old valves, and it's a very useful teaching aid to show you what's actually happening inside. Excuse me. So this is the pilot operated pressure relief valve operating against this spring, 20 psi spring, to give us greater efficiencies in our system. Another advantage is by acting just against this 20 psi spring instead of this great big 3000 psi spring, I actually get better control. I get more gradual opening and closing. And where there are pressure variations in the system, it's going to be detected easily and shut down quickly. It's going to be more responsive in my system. So if I have a sudden burst of pressure, this valve will actually close a little bit quicker as well. And these diagrams are just talking about, with the green arrow showing the fluid flow, what I just explained, what's going on. And here we have it in a system. Okay, how could we use one of these? Now this is for the vent connection. Remember I said there was this other piece here on the left that we could use. It's different types of uses. In this case here, we've got an unusual configuration of a valve being used. This symbol is the direct acting, the simplified version of the valve, but we know that port 3 is available if we wanted to. So in normal operations, if I look at this as being normal operations, remember the spring on the valve here, the 2-4 valve at the bottom, 2 positions, 4 ports. Even though 2 ports are blocked, we still refer to those as 4 ports. It's holding it in this current position here. So what will happen? Well, if I run the motor, fluid wants to build up pressure, but if I track back through this valve from tank, there's low pressure here. There's low pressure at this point on the valve. What that means is if there's low pressure there, it's going to allow the main spool to move upwards. It's as if this was cracked, as if the pilot was open. I've got low pressure here, a little bit of fluid allowed to leak out through my system and back to tank. Therefore, this configuration, all the fluid flow would be dumped. Okay, wouldn't be allowed to operate. Now, if I turn a circuit on with my electricity and I engage this solenoid, I switch it over from the position shown to this other position here. P would be connected to B, which is blocked off. T can be connected to A, which is blocked off. Therefore, there's no fluid flow. Therefore, pressure is allowed to increase and the system will operate correctly. This is a configuration we often use in an emergency stop. If I lose power, this valve moves back to the shown position, causing my pilot operated pressure relief valve to fully open because there's no pressure on the remote, dumping all that fluid. Okay. Also, I have, in this case, drawn, if you remember back from Mac 205, this symbol that I've got a push button of some sort. I can push the button on the valve and cause the fluid to automatically go from the pump back straight through the reservoir. So it's a good use as an emergency stop valve here using a pilot operated pressure relief valve. This valve over here that we've drawn would be called the emergency stop valve, even though it's a 2-4 valve, and this would still be called my relief valve because of their functionality. Remember, we call our valves based on their functionality. So this is one of the uses of using that vent connection. Okay, now the other connection here I have is a remote control. So I have my main valve, my main body, and I have set on this a maximum relief pressure, but I may have another pressure that I want an operator to be able to reach, okay? And I may want the operator to say, listen, turn this down from 1000 PSI to 800 PSI because today we're running a copper product through our system. Okay, for some reason, we're doing copper survey plates instead of steel survey plates. Why would you do that? Well, if you're in an explosive environment, we'd like to use copper instead of steel. It's not going to spark. or brass, even better, not going to spark. Therefore, we may change the material. We don't want to damage it with the same amount of force that we were printing the plate before. So the operator may have a remote adjustment in order to be able to set the maximum pressure in our system. This is very old fashioned. Nowadays, it's all computer controlled. The automation guys will actually program this and have a system where the operator can do this electronically instead of manually. We still use this remote port. We're going to get into that, but we don't usually use a valve anymore. But this is still technically correct for what we're actually doing. What we're really going to use is an electronic solenoid nowadays. I'm not going to do this on our labs. We're just going to play basic hydraulics. We're going to use an electronic solenoid as the remote to set the maximum pressures. And very common to have multiple different settings that we can have, or an infinite setting. So the example we're going to use here is a 3 pressure setting. Okay, so I have a circuit very similar to what I had before, okay, where I'm going to clamp something, but in this case, I've got a more sophisticated pilot operated pressure relief valve. In the bottom here, we can still see the regular old pressure relief valve, but you'll see I've got 3 different pilots. Okay, and I've preset these pilots here to 800 psi, 500 psi, and 1500 psi. I might be clamping plastic, I might be clamping rubber, I might be clamping steel, and they're going to each want different pressures. If I look at this valve just as is, okay, what do we see? Fluid comes down, wants to go through the valve. Okay, can't go through the valve. I've got some sort of remote operation that is setting the pressure here. Oh, in the normal position, 500 psi. 500 psi is activated. Okay, and so pilot heads 1, 2, and 3. Pilot head number 2 controls the pressure when neither solenoid is energized. Remember this A and this B. These are my electrical symbol for a solenoid, well, my pneumatic or hydraulic solenoid, as opposed to what we had in our MEC 205 electrical drawings. Neither one is activated, so therefore the springs hold it in the center. If I activate A, push this position over, that means the fluid coming through will go through there, if I remember correctly. Nope, it won't. Okay. If A is energized, 1 will actually activate through, because it's going to come down through this arrow and allow the pressure of 1500 psi to be set. So this is more typically what we'll have as preset levels. It's a cheaper solenoid, have preset levels, and electronically will activate A or B or neither and get the maximum pressure in our system. Now, what we've got here is an electrically modulated system. If I think about before, I talked about a basic relief valve. We have a pilot stage, okay, which has a maximum pressure, and remote stage is this proportional pilot stage. Now, these valves are stacked on top of each other. We call them a stack valve. We're really, really creative when it comes to hydraulics. Okay, they're stacked together, we stack them up, we call them a stack valve, to achieve the same operation. Instead of having lots of plumbing and piping going in everywhere, the plumbing is built in to the steel body of the valves. But look at the symbol, it's a little bit different here. Okay, this symbol is simplified. Okay, what we're showing here on the left in the symbol is a simplified drawing of our pilot operated pressure relief valve, which has a setting in it. That's this maximum, this backup pilot stage, which once again is going to be hidden away and set my absolute maximum pressure in the system. And this electronic relief valve, this electronic proportional control valve, indicated by this arrow through the electronics, okay, is going to give me infinite adjustment. Okay, so I'm going to use 4 to 20 milliamps to control this. If I look in this cross section, you can see here, because I've cross sectioned it, 2 bits of the winding that we're using to control this proportional stage to be anywhere from fully open to fully closed. What I can do is I can set this pressure anywhere from 20 psi through to the maximum setting allowed by this backup pilot stage. Or typically this is what we're going to do nowadays in our electronics. So it's a little more sophisticated, gives me infinite control, so I can design my process appropriately. As things start wearing out or whatever, I may want to increase the pressure a little bit or decrease the pressure a little bit. I can do that. I can, instead of saying run at 1500 psi, I want you to run at 1550. It's just a little bit of programming, nothing else that needs to change. So this proportional pilot stage is the equivalent of my remote. Well, it is a remote. I've just got an electronic remote nowadays that is going to control the main pilot area. But in between, I have this, what we call a backup pilot stage. This is my absolute safety, my maximum pressure that I'm going to allow in the system, and no programmer can override it, so that the operators are kept safe. Main stage, I talked about that, the intermediate stage, or this safety pilot stage, and this proportional stage that is electronically modulated. Slip-on cartridge valves, we'll talk about more about that about week 8 or 9. And set this relief pressure higher than my operating pressure. Really, this is going to be set based on the need of the system and the need of the operations. It's set so that someone can't override the maximum pressure. Can be controlled from a distance or a location. Now, usually I've got a controller on my press, my injection molding machine, whatever it is, but I can usually override that if it's hooked up to my network and change the program and shut it down if necessary. Okay. Any questions before I carry on with this idea of these relief valves, because I'm going to move into the other valves? Any questions?
No questions.
Okay. So I'm going to fly through a lot of this other stuff a lot quicker, because I've talked about the basics of how a pilot works and the basics of how a lot of the internal mechanisms work. And this is common in pressure valves. So I'm going to move to the rest of the material a lot quicker now, because the theory and the operation, we've covered it over 50% of the theory of the operation on every pressure valve just by covering this pressure relief valve. Okay, so an unloading pressure relief valve is just a pressure relief valve used as a different purpose. So we're going to unload our flow and pressure in a circuit. Some circuits we want to do that. So I can use actually the same valve as an unloading valve, just a different use, or it can be a little bit more sophisticated about it. And this one has a check valve. So if I look at this valve, it's two parts. I've got my pilot operated pressure relief valve, okay, even though the symbol doesn't draw it that way, but I can really tell because there's this extra remote line available, okay, and I've got a check valve. That's what this piece on the left is. It's this check valve symbol here that you should remember from MAC 205, okay. What it's going to do is limit the maximum pressure, and it's going to allow us to unload the circuit, take away a lot of the flow of a circuit when we don't need it. Remember, from weeks 2, 3, and from weeks 2 and your labs from weeks 2 and 3, we had these equations about horsepower. Horsepower is basically, or any power, regardless of a metric or other, can be calculated based on the flow rate of my system and the pressure under which that fluid is operating. So the amount of horsepower to drive a pump is based on pressure and flow. If I can maintain that pressure and dump the flow when I don't need it, the horsepower is less. I've spent less money in my system. The horsepower is less. That's less energy going into my system. That's less energy if the system isn't moving. That had to be converted into heat. So I've got less heat in my system. The part's going to last longer as a result of that. The oil is going to longer as a result of that. So it's really good to divert flow, to unload my system if it doesn't need the flow. So unloading valves are very common if I have a fixed displacement pump, and that's what we're kind of using in our first 9 labs. We talk about a fixed displacement pump, and we have to accommodate that pump. So that's what's going on with this. And let's have a look at this valve, how it's often used with an accumulator. Remember back to MEC 205, I talked about an accumulator. Okay, it's like a balloon. If you blow a balloon up, I've stored air under pressure. It's the same with a hydraulic system. When we get to accumulators, you're going to see some of them are pretty much like a balloon. Okay, we act against a bladder and increase the volume of fluid stored under pressure, much like an electrical capacitor or even the battery in your phone. We've stored potential energy. Okay, I've stored this fluid at pressure, and I may want to do that. In this case, it's going to the system. I may want to hold something in place when the system shuts off. There's a bunch of different things we can do, and this is why this valve is kind of interesting. It is allowing us to charge the system, and when the system is fully charged, it's going to build up pressure, cause it to open. This check valve will close as the pressure drops on this side over here, and cause fluid to be dumped back to tank. It's just another pressure relief valve here, except instead of having a remote, we've got a check valve doing that work for us in conjunction with an accumulator. And this is just one use of this, not the biggest use, but it allows this accumulator to be charged and maybe hold pressure in a system while all the excess flow is diverted, saving us money. A little bit of detail here on pressure areas. These are incredibly small. Okay, these are really, really tiny. We're talking thousands of variation across a surface area, across a diameter. Well, that equates to a bigger or a smaller surface area. Acting with the same pressure, that little tiny poppet is going to move and cause this to open and close. Pressure reducing valves, next one. I'm going to come back to other unloading circuits later on where we'll use this. Pressure reducing valve, okay? So the idea here is to maintain a maximum pressure in a system. The operation is very, very similar, except if I look at my drawing, the pressure line is downstream. It's not upstream. I'm not looking at the upstream pressure to control this. The other thing is it's drawn, you can see with that line indicating that poppet or that spool, it's drawn in a normally open position. So this valve is normally open, and if the pressure gets too high downstream, it's going to act against the poppet, closing the poppet, therefore setting a maximum pressure downstream. So I may have a system running at 1500 psi. Yeah, absolutely fine. But I've got something that I only want to run at 400 psi or 200 psi. So I use this pressure reducing valve to do that. Okay, so if I'm clamping something really, really light, okay, that I may want to just clamp a piece of aluminum. I don't want to damage it. I'm going to use some low pressure, but I want to punch a hole in it. That requires a lot more pressure. So I have this low pressure part of the circuit operating the clamp, leaving high pressure for the rest of the circuit to operate that punch. So it's a normally open valve. It senses downstream. And the other thing to note is this external drain. It's going to require a drain to operate, and that's looking at the details inside that valve would be able to see why that is the case. Sorry, this is at the bottom, and it's drawn off the spring side, sometimes from the spring, sometimes just from the box on the spring side, to indicate a small volume of fluid, no more than a cubic inch per second, often less, is going to be required to escape through a drain in order for this valve to operate. If you don't connect this up, this pressure reducing valve locks in the open position and does not reduce the downstream pressure. So here's a use case for it. Okay, a pressure reducing valve. I've got a clamping circuit here. Let's say that the top here is the clamp. It doesn't say it, and the bottom is going to operate a drill or a punch or some other operation. As drawn, the circuit oh, all the flow goes back the tank through this tandem circuit, no pressure builds up. If I activate this valve, so now pressure can flow into the line, flow out of port A. It's going to go towards this valve, which is normally closed. It's going to go towards this valve that's normally open. Path of least resistance goes through the open valve. It's going to extend this cylinder. When the cylinder gets fully extended, pressure, or when it clamps on something, pressure will build up. And when it builds up high enough, the valve would then close. Excellent. That valve is now closed, allowing our system to maybe open this valve. This valve here, you can see, is looking at the pressure on the inlet side. So as the valve and pressure increases, it's going to open this valve, allowing fluid to go through and extend that cylinder as well. It gets fully extended, maximum pressure builds up until the relief valve kicks in, allowing the fluid to get dumped back to the reservoir. Kind of wasteful in energy, but this is how it works. I reverse the flow. I'm going to have then fluid going through B. It's going to go to both cylinders. It's going to try and push fluid out of the cylinder. In this case, through a check valve, back to tank. In the bottom, through a check valve, back to tank, allowing these two cylinders to retract. Excellent. I've set a maximum pressure in this top cylinder. Excuse me. Valve looks very different, but it's still pretty much a pressure relief valve here. The difference is in the operation. I've got this spring that I'm acting against, and I've got this pressure that I'm acting against. Okay. Now, if this outlet pressure increased to spike due to someone pushing back extra on the load after its operation, the pressure would build up. If there's a system shock, something drops onto a conveyor, like in the oil sands, there's a shock to that system. And, we're dropping 5 tons at a time onto these things. We want to accommodate that system shock. So a little bit of fluid allowed to escape, okay, because fluid's virtually incompressible, drops the pressure. So we have this hole that allows a little bit of fluid to drain, okay? As a result, I need to always have a little bit of fluid draining through there, that a hole doesn't open and close. So what really happens with my pressure reducing valve is it always leaks. There's a little bit of fluid flowing through there, and that's fine. I'm going to get a little bit of a balance, and this valve is going to sit at that point where just enough leakage going through the system is going to go through and operate the valve and hold the pressure. If I've got a little bit of leakage in my cylinder, blow by, okay, it's going to be fine. This valve will accommodate that. So that's why we have this high pressure line operating against the surface area to move this spool backwards and forwards, and this dotted line, this small dotted line coming off the valve on the spring side going to drain. If I block that, I can have a pressure lock, and this valve doesn't move, it stays wide open. Some slides going over that detail. Direct acting pressure reducing circuit. Okay, it doesn't matter if it's direct acting or indirect acting, it's just the efficiency of the valve that's going to be different. So this circuit here is designed with a clamp. That's what this one at the bottom is. It's going to set with a maximum pressure, and then at some point we can activate. In this case, I think it's meant to be a drill, drilling a hole through a pipe. Really badly drawn circuit, this one. This came out of an old Vickers manual. There's lots of omissions in this drawing. Now, of course, we can have pilot operated as well. I'm not going to go into detail about this. This pilot stage, once again, is a direct acting pressure relief valve, okay, acting with the pressures. And once again, because it is pilot operated, I can use a lower pressure spring in this main valve body. That's going to give me excellent modulation. So for a pilot operated pressure reducing valve, I get a really nice flat line of what that maximum pressure is. In a direct acting, that pressure is going to vary a little bit. It's going to be very unstable because acting against that big spring on its own. So a pilot operated system here doesn't give me a lot of savings as far as energy is concerned, but it's going to give me better control of my system. Nothing new there. These next few slides are all going through the same thing. There is a small video here that you can click on link. If you click on it in the slide deck, if you download the slide deck and click on it, you'll get something just this size. If you click on the link that we've built both in, that'll take you directly to YouTube and open it up and give you full size and full control. This is part 1 of 2 of pilot operated pressure relief. If you are struggling with the concept, you can go to and have a look at this and then links to other slides. I'm not going to play that. I'm going to move on, try to get through this on time today. Built in with an optional check valve. Because if I'm trying to push fluid back through the other way, well, yes, I could technically. I could pressurize here and force this to be open and allow the fluid to go through the other way. It's not designed to do that. There's going to be more wear and tear, and it's going to respond slowly. So it's better to build in this little check valve as the pressure builds up. Okay, you'll see there's holes in this check valve that allows the fluid to flow through. If the reduced pressure side over pressurizes, i.e. I reverse the process, I'd get the high pressure where the orange currently is, pushing up against this check valve, against the spring, causing it to open, allowing fluid to go back again. So very cheap to build in a check valve, $15, $20 to build to the additional cost. And a check valve on its own is a couple of $100. So we build it into the valve at very marginal cost on a $300 valve, allowing us longevity of our system. Now, the valve in this drawing is an very old-fashioned valve. It was called the Vickers valve. And a Vickers valve is a pressure control valve that you can reconfigure. So if I look at this valve, it's actually got different parts. There's a parting line here. Okay, if you remember from your drawings, there's a parting line here that shows the 2 separate parts. So if I put this back on, the top piece on the other way around, well, this drain passage is not connected. Same with the bottom, there's a parting line that I can put on the other way around. I can take this apart and actually change the spool in the center. I can put on a different part at the bottom. So a Vickers valve actually comes with 5 different parts, and I can build with this over a dozen different types of valves. Excellent. This means that, say I'm in northern Alberta working on a project and a valve fails, well, I don't have to wait for this part to come from Edmonton. I've got a few spare parts available, a few old valves kicking around, and I can just change out the part or reconfigure the spare valve for my operation. So that my parts that I had to carry was considerably less, and this was a big advantage. We don't use the Vickers valve anymore. Our price of manufacturing valves and the technology that we use to make valves means that the prices come way, way down. Transportation's also better. If I really do run out of a valve, I'll get a plane to deliver it if it's a big operation. Yeah, we'll do that. So we actually got donated so many of these over the years. I think we did a clean out down in the Millwright lab about 3 or 4 years ago, and we had 130 of these that we threw out because we've been given so many over the years because they're not generally used. But from a teaching tool, this is fantastic to look at this valve and look at how it operates. So this old Vickers valve we can use to create back pressure. We talked about an unloading valve already. I can convert this to an unloading valve. A sequence valve, okay, well, that's what we're going to talk about next. A counterbalance valve and a brake valve are the valves we're going to talk about that I can build out of this thing, okay? And I like using it because if I keep using the same valve over and over again, with luck, you'll learn better what the capabilities are for a pressure valve. So here we have a circuit, and I'm going to set this up as a back pressure valve. I want to create back pressure sometimes. So if I think in the case of a linear actuator or a piston in a cylinder, if I don't have any back pressure and I suddenly apply flow to this, it could lunge forward. Okay, lunging is generally not considered a good thing. We don't want to maybe have it move forward quickly and do some damage as it hits something that's a little bit brittle. So we want to be able to make it start and move under a controlled manner. And often we can do that by creating some back pressure in our system. Okay. This is like metering out in our MiG-205 pneumatics. Now we can do this with a simple check valve. I've got a little check valve with a spring in it that's opening at 35 PSI. That's nice and great. That works absolutely well. It's way cheaper. But if I want more than that, if I want a couple of 100 PSI, we don't make check valves that big. So I want to create this back pressure valve to create some back pressure. The other place I might want to use this is if I am creating a rotary system. Okay, I don't want it to freewheel on its own. I may want to have a little back pressure so that someone walking past it or vibrations are not going to make this rotate unless desired, unless it's under control. So a back pressure valve is desirable to gain better control of my circuitry. Now this is the same valve we had differently. It's just been printed backwards from what we had before. I've got a nice picture here of a big spool valve with a pilot control and an electronic control in order to be able to control large volumes of fluid. The spool is not shown. That spool that would be in this big gap would be the center stage here, showing what we can do with it, what the three positions would operate. Not important for this drawing really. What's important here is, say at this stage, the fluid flows through from the center position, flows into the valve. Okay, a bit of back pressure will build up, forcing this valve to open. Okay, allowing the fluid to pass through. Well, it doesn't really just act on the surface. The surface on the top of the spool here, or the inside of the spool, is the same as the surface here. I've got balance forces acting on the spool, so it ain't going to move. Okay, but I do have this little channel here going up under this little piston. So I've got this little extra surface area. Okay, so bigger surface area here plus here, causing the valve to open, allowing the fluid to go through. So it's going to open based on the spring force, whatever I set that to. Okay, and allow it to open and run. Okay, so pretty much the same as the pressure concept we were talking about for our pressure valve, our pressure relief valve that we first talked about. More surface area, add a pressure, opens, lets fluid go. Not a biggie. Okay. This is just talking about the way it's assembled and the way that that pilot works in order to operate the valve. Now I've got a different valve here set up as an unloading valve. Sorry, the same valve in a different configuration. You look, we turn the bottom around. So instead of using an internal line, I took out the nut at the end and I have an external line available for unloading. Now before we talked about unloading for a circuit to unload the entire flow of the circuit in order to save money. In this case, we want to unload one of the pumps. If I think about a hydraulic circuit, if I want to move something really quickly with a lot of flow, okay, that's excellent. I may be moving something very quickly, but as I get towards the working part of the equation, I may want to clamp something. That doesn't require a lot of flow, but I still need the high pressure. So if I can dump most of my flow at low pressure and just keep a little bit of that flow maintaining high pressure, I save money, because remember, horsepower equals flow times pressure. So in this case, we have two pumps and there's a check valve between them. So let's start off explaining this circuit in this default position. Both pumps are running. Okay, 45 gallons and 5 gallons. There's no pressure in the system, so the check valve is going to be wide open. There's no pressure being detected here, so this valve is not going to open. Okay, this valve is going to stay closed. There's no pressure detected, so the pressure relief valve is going to stay open. But then we hit a block. Oh, there's nowhere for the flow to go. Okay, pressure is going to build up, and this is going to dump all my flow, 50 gallons per minute, at whatever this pressure relief valve setting in. So say I've set this to 1000 psi. Okay, what I do is I set this unloading valve at a lower pressure, a pressure between, okay, my working pressure and my safety pressure. So say I actually need only 800 psi here. I've set this to 1000 for safety. I set this down to 600 psi. So what happens is, okay, 600 psi, this thing fully opens. It dumps all the fluid from the 45 gallons per minute at low pressure, 600 psi. Well, how about I take this a step further? If I think about it, why am I setting 600 psi? I want to set this low, just above the pressure required to make this thing move up to the item that it's going to clamp. So that might be only 100 psi. Excellent. I'm going to save a lot more money when I dump 45 gallons a minute at 100 psi than trying to pump 45 gallons a minute at 800 or 1000 psi. So the system is closed. 45 gallons a minute is getting dumped at 100 psi. The setting on this one, 5 gallons a minute is, oh, checked, can't go that way, at high pressure. That high pressure, keeping this valve wide open, that high pressure being dumped through my pressure relief valve. Wasting a bit of money, but certainly not what we would have been if we'd been running 50 gallons a minute. Someone opens the valve to make the clamp move. Pressure drops. Excellent, the pressure drops. I want to move that thing quickly as possible. The pressure drops. Okay, therefore this valve closes. The pressure here is lower than the pressure that would be generated by this. So now I've got all 50 gallons moving my cylinder across to do a good clamping job for me. Excellent. We get full length of travel. We clamp against something. Pressure jumps again. Pressure jumps, causing the valve to open at 100 psi, dumping 45 gallons a minute at a low pressure. Unloading. I'm unloading most of the flow of fluid of the circuit, allowing just the 5 gallons a minute getting through this high pressure, 1000 psi when this clamp is fully extended. Wasted energy. Instead of 50 gallons a minute of wasted energy, it's 5 gallons plus a little bit, whatever the setting is here. So I only use the small pump to do the heavy lifting. I use the small pump with the big pump to do the quick lifting, the quick work that I need to do in my process through using this as an unloading valve. Same valve, just instead of internally sensing that we used last time, we externally sense in our circuit. And then there's a few slides going into detail on that. Sequence valve. Now we used a sequence valve in MEC 205 with pneumatics. The design of this is radically different. We're doing a lot of bigger operations, higher pressure. So it's a very different design, but it's going to achieve the same result. I want a sequence of operations. I want one thing to happen at low pressure, allow the pressure to build up. The next sequence of operations can occur. Okay, and in hydraulics, there's a lot of pressure available, so I can have quite a few different items in my sequence. I talked about a 4-sequence operation earlier of moving the steel, clamping the steel, punching the information, cutting off the steel. You can do this with a bunch of sequence valves and hit go. Okay, instead of having to have a really sophisticated operation that we would use today, we don't technically do this. And I'm talking about this particular operation because actually once I rebuilt a press that was about 60 years old, the control systems had all failed. They're just worn out. So hydraulics doesn't last forever. But the press, I estimated this press is probably good for 200 years. Okay, it was built in 1940. We'll probably still be operating in 2140. We put in a new control system with a new sequence of operations, all electronic, because the old stuff had worn out over 60 years. Okay, so it's a real world example doing that operations, and it was all done with these sequence valves. And a pressure reducing valve to set the maximum clamping pressure. So in this sequence valve, the bottom is still realigned for this internal sensing. And okay, imagine there's a nut in there holding that closed. Well, that's the light gray. And what we've done is we've turned the top around. So instead of using the internal sensing line, okay, I'm actually going to use it as a drain. I'm going to use that sensing line just as a drain by turning this around and building the valve slightly differently. So the sequence of operations, imagine that this directional control valve is wide open. Once again, a bad drawing because it's showing a pneumatic directional control valve, not a hydraulic one. An old drawing. But the fluid, say it was open, allowed to flow through to the clamp cylinder. Okay. This flow path here is complete. There's a hole in this check valve poppet that allows the fluid to go through it. This is a cylinder in a big wide open space, so fluid can go around it. Okay, fluid can even go through this small hole, allowing fluid to go to the clamp cylinder. This top part here, well, that's closed at the moment. I don't have enough pressure to build this up. Okay, so there's nothing going to the punch cylinder. Fluid goes through to the clamp cylinder, moves the clamp over, clamp gets to the full extension, clamping against something, can't move anymore. Trying to make pressure flow, resistance to flow means an increase in pressure. This increase in pressure acting upon these two surfaces doesn't do anything, but I have a small pilot line, a sensing line under pressure acting upon this little piston, which is also going to act upon this big piston. Combined area is bigger than the area at the top under the same pressure, meaning more force to move this spool upwards against the spring, allowing fluid to now flow through to the punch cylinder. Okay, if I didn't have this drain line hooked up, the fluid that would be trapped behind here would be trapped. Okay, it wouldn't be able to move anywhere. Okay, so a little bit of fluid can escape through the line. As this moves back, it's going to actually suck in a little bit of fluid back out of the line. Okay, so the little bit of fluid there that moves backwards and forwards over the operation doesn't really go anywhere, but it needs to be opened to air. We don't open things directly to air. I don't want bugs getting in. I don't want dirt getting in. I'm going to open it to the drain, and that drain going back to the top of my reservoir, the tank, where there's air. Okay, so I've got controlled air, clean air connected up to this, and allows it to function. So I've built a sequence valve, okay, by getting rid of this internal sensing line at the top and turning it into a drain line. Same valve, same concept. Okay, when I want to retract it, I push fluid out of the punch cylinder. Okay, it will come through, push against the check valve, back to tank. Same with the clamp cylinder. Well, it's directly connected. Sorry, it's connected this way. Back to tank, punch cylinder, through the check valve, back. Oh, this is a bad drawing. Yep. Back to tank. Yes, there, that way. I misread that. Fluid coming in, pushing the cylinder back, fluid coming through this main pressure line. The check valve is open, and it's also got this hole through it, allowing fluid to go back through to the reservoir. Sorry, missed up that one. And then more talking about the pressure sequence valve, the symbol for this pressure sequence valve. I am detecting downstream pressure to act against the poppet, which is acting against a spring, which I can set and has a drain line going back to it with a built-in check valve. We saw this earlier, about 8 to 10 slides earlier, in our circuit that we had built with the pressure reducing valve. We also had a sequence valve. We didn't talk about it while we spoke about it. I didn't say what it was called. I just described the theory of operation that allowed the clamp to come out and hold the circuit, hold the item while another part of the circuit did its job. And that valve was the sequence valve. More discussion about what I just talked about. Here's a variation. Okay, if I turned the bottom around, remember, I used this internal sensing line at the bottom to detect when the pressure in the clamp circuit was high, causing the valve to open to allow the next sequence of operations to occur. If I turn this valve around, okay, I get an external sensing line. Now, I can't do that with a general sequence valve like we have in the lab. I don't have an external sensing line available. I can buy them that way. But if I want an external sensing line, I could do this very easy with a Vickers valve. One of the beauties here, if I look at this clamp operation, I may not want to monitor the amount of pressure in that system. I may want to monitor that the clamp is engaged. If I think about that, if I'm clamping an object, I've got some object and it's got different, properties. It may not be the amount of force that I want to clamp. I just want to clamp this object to a certain distance. They're all the same. They could be made of a thin wall plastic. They could be made of a SCARED 160 plastic, steel, SCARED 160 steel, all different strengths. So therefore, I just want to clamp to a certain distance. So in this case here, we clamp to the certain distance, and that is detected, okay, as my sensing line. Excuse me, as my sensing line, allowing this valve then to operate the next step of the sequence. So I used a pressure valve monitoring a distance, okay? So I actually created a pressure system that way to activate the next sequence. One variation of how we could set up our circuits. We could monitor alternate points, and that's the beauty of some of our pilot lines that we have. And the only valve we have access really to that pilot line, converting it from external to internal, is the counterbalance valve, which is the next valve under discussion. So the same Vickers valve, okay, set up in the same configuration as I had for my first valve, okay, my reverse pressure valve. I can't remember what I called that valve. I'm going to set up this valve instead of over here to create back pressure, okay, I'm creating back pressure near my point of work instead of for the whole system, just as this item here. So if I imagine a system here where I've got something coming down or something that I want to hold up in a certain amount of height, so think of a scissor lift. Okay, a scissor lift, you've all seen the genies and the scissor lifts where a couple of people get on it, we lift it up high and we do some work at altitude in a building, maybe on a 24-foot ceiling, put running some pipes or some electrical lines or something like that. We need to bring it up there and we want to lock it in place. We want to lock it in place so that we don't have to waste any energy continually running the machine. And you'll see this. The guys are up there, they're working on some electrical, and the machine's turned off. No energy getting wasted. It's held in place. It's held in place using a counterbalance valve. So I've got this load. In this case here, I'm talking about a load going up and down. Same concept. At this stage, I've got a certain amount of load pressing against this spool and against this pressure line. If I set this to be just a little bit more than my load, okay, say this is a load of 1,000 pounds, and I set this to be 1,100 pounds. 1,100 pounds is not being seen, therefore it won't open. But as soon as I try to push this down, I get fluid coming into the top. Okay, I'm getting pressure, flow against an area. I'm getting extra force in addition to this platinum at the bottom, creating extra force at the bottom here. This area is under pressure, creating a total force that now exceeds the force of the spring, allowing this valve to open, allowing this to be pushed down. In the reverse direction, I pump the fluid through, pushes the check valve open, lifts my load up. Okay. So I've got drawn here the valve configuration, an internally sensed pressure line. Okay. And then I've got a check valve for the reverse flow. So this is good for loading, holding a load up. Okay. In place. A little bit more about that. The internal sensing. Once again, internal sensing. Once again, there's a video. I would recommend actually going and watching this video and then watching it again after we cover some of the things that are maybe lab 8 or so. Come back and watch this again. I'm not going to bother playing it. It's available for you to play it. I want to move on to this counterbalance with the external sensing line. Okay, so this Vickers valve is now being configured by switching the sensing line to external, okay, instead of having the internal line. And that's why it's showing with this line now, this pressure line going out of the valve body. It's external. The beauty on this is that I don't need to over pressurize the valve. Remember earlier I said you've got to have the weight, the pressure from the force and the pressure from this adding together to force this valve to open. A better way of doing it, energy-wise, is as soon as I detect that I want to push this down, okay, I'm going to have an increase in pressure, which is going to force the valve to open straight away. It's going to open at a lower pressure. It's going to be more energy efficient. If I turn the system off, there's low pressure here on the external sensing line, not acting against this little piston. I've got pressure generated by the load acting in an equal measure against this main spool, therefore will not move. I'm achieving the same thing using an external line, but when I'm trying to move the load down, I don't need to create as much energy because I'm generating less pressure in order to get this to move. So I've got a little bit of an energy saving. So the external line can be useful there. Now, typically we don't use devices like this anymore. Just internal or just external. Generally, a counterbalance today will have either just an internal or both an internal and an external. And that's for safety reasons that we're going to do that. And I'll talk about that probably a little bit later, or maybe in the lab when we do counterbalance valves, about a couple of deaths due to the wrong valve being installed. So whether internally or externally, it's still going to work. Just there's some advantages to the external over the internal. Same valve again, well, not quite the same valve. Okay, being used as a brake valve. Remember I said you can get different spools, and this is using a solid spool. Okay, it's going to give us a little bit of a difference in performance. Now here I'm using as a brake valve. Same position as I would have used, say, a counterbalance valve. Instead of using this to hold a load, I've got a rotational item, say a big wheel with a lot of weight behind it that I'm rotating. Think of the conveyor belt systems at the oil sands mines. Okay, they're carrying how many tons of sand at a time? Okay, there's a little bit of momentum there when I'm carrying 15, 20 tons on the conveyor and it's being driven by this hydraulic motor. If I wanted to stop because someone fell in, I wanted to stop it pretty quickly. So I want a decent system to stop it. I'm going to use a brake valve in order to really slow that thing down into a controlled stop. I don't want to have a shutter stop boom, that might cause a pressure spike and cause some damage. Okay, it might cause the person who fell in to get injured. I want to stop fairly quickly, but in a controlled manner, like braking a car. It's better to brake a car, okay, under the brakes and crash into a wall and come to a stop real quick that way. So we're going to do that with this valve. Okay, so I've got the system running here. Look, I'm using a fully open center instead here. So if I try to pump fluid through, there's a bit of resistance. It'll just go back through the tank. Nothing happens. But if I activate this to get this load up and running, pressurize the system, get fluid to flow through into this valve. Okay. Oh, got to pressurize. A little bit of internal sensing to help maybe get this open. Well, remember we talked about with the counterbalance valve, that was a little bit inefficient internal sensing. If I have the external sensing as well, well, we didn't have that before. I've changed the bottom of the valve as well to have both internal and external. So I've changed two parts of this valve in order to make it function. Soon as I get some pressure up here, which will build up as I've got resistance to the motor rotating, it'll cause this valve to open because this external line is acting on this full area, not on the small area of the internal pilot line. So bigger area, less pressure required to get enough force to force this to open, to allow fluid to flow through, to allow the motor now to turn. So we're going to build up speed and get this thing running. Excellent. If it tries to overrun a bit, what will happen? So I've got some reason this is trying to run faster than my desired operation. It'll try to suck fluid through. Okay, if I want, I'm trying to feed it 4 gallons a minute, but it's trying to draw 5 because it's overrunning. It'll suck fluid through, causing a pressure drop, causing this valve to close, causing the fluid flow to slow down. So it prevents overrunning as I'm trying to accelerate or get up to speed. So I'll get a nice curve up to an acceleration. I won't get this over speed situation occurring. Excellent. Get up and running, nice. It modulates, it maintains good speed. And then when I try to shut it down, okay, when I shut it down, this valve is in the stop position. Well, it's fully open. Fluid is free to flow. So I turn this off. There's no flow really coming from the pump. It's going to take the path of least resistance back to drain. I've got this fluid being pushed through by my motor, which is now acting as a pump. It's trying to draw fluid from part of the system and push it through the system. It's going to get a high pressure, pushing that fluid through the system, opening and closing, allowing the fluid to go back, recirc, back through the same pump. So I've got the momentum of this thing running, pushing against my brake valve to cause it to open a little bit and let a little bit of fluid through. But this brake valve is only letting a little bit of fluid through. It's braking, it's trying to prevent the flow of fluid, okay, fairly effectively, because I've only got this small surface area here trying to force it to be open. So it's going to bring my rotary item down to a controlled stop, even though this is an open valve, okay? The center is open. Internal and external sensing, I talked about how those work, okay? I talked about how operating the motor to accelerate it, braking it. What's the time here? Okay, I'm going to say watch this on your own. I'm just going to start it to show you what's in this little video.
Welcome to
Simplified symbol.
So if we look in this circuit above the pump, we've got a pressure relief valve. What we're trying to operate is a clamp and a drill circuit with 2 individual directional control valves. Now, we talked about earlier about using a pressure reducing valve to make the clamp work and then hold it at maximum pressure, and a sequence valve to make the drill happen afterwards. This is a little bit more sophisticated, what he's discussing here, because it's also including a sequence of operations to return it. Realistically, I don't want to unclamp before I try to pull the drill out, because the drill will get stuck in a piece of steel. I want to pull that drill out while it's still running, ideally, out of the piece of steel before unclamping the piece of steel. So that's why there's a second sequence valve here on the retraction of the clamp. The drill has to retract, build up pressure, allowing the clamp to return. So watch this video. He is going to talk about pretty much exactly the same things I've talked about, just from a different person. Same sort of material, talked about in a slightly different way if you're having trouble, to help you out there. Any questions? Any questions? Can someone confirm you can see my screen with the breakout?
Yes.
Excellent. Okay, so your breakout number 2. A lot of it's very similar to breakout number 1. How are you going to solve this? Question 1. Okay, if I go back through my problem-solving methodology, read the question. What is it we're trying to solve? What is the pressure gauge reading? So we're really after what P is. Let me turn on my pen. Should be able to turn on. I just recharged it. Yep. What is the pressure? That's what we're really about. Okay. We're given force, and we're given a diameter, and one additional requirement, asked for the answer to do 2 decimal places. A little extreme considering the forces involved here, and the, we're not going to read a pressure gauge to that, but the thing we're trying to reinforce here is, what did the customer actually ask you for? Too often customers have asked for something and someone has not delivered. I had a colleague fired at Honeywell because he did not deliver what the customer asked for. It turned out, as a result of doing that, it didn't work for the customer. So, $14,000 item the customer ordered and purchased and didn't work. Someone had to take the fall for that. Okay, so the colleague who did the design work took the fall for not actually giving them what the customer wanted. So we're going to have here a simple equation. Force equals pressure times area. Okay, so I'm going to get area equals pi d squared over 4. And if I combine those together, I'm going to get my 250,000 pounds over an area of about 78.5 square inches. And I should get an answer of somewhere around 3183.09 psi. Now, you may get a slightly different answer to what is given in these breakout sheets. And that is because I've noticed Steve, who put this together, does not carry forward as many decimal places as I would. Okay, so in this sort of answer, I'm going to be carrying forward a lot more decimal places on my intermediate steps, or just do one great big step like I often like to do mathematically, and I will get an answer that may differ slightly from him. Don't really worry about it. When you get to the quizzes, there should be some rounding errors built into one of the questions. I do have to look at one of them. Someone had an error they pointed out today, but I didn't get to look at it in time. There may be a rounding error. So don't worry if you're really out a little bit on these exercises. So simple solution, we covered this to death in breakout number 1 and in some of your labs. A little bit of a different situation here. I've got a load trying to go down. Okay, I've got a closed valve and a pressure gauge. So my force is acting on an annulus area, not on the cap area. Same equation, force equals pressure times area. Okay, but my area is acting on the annulus, so it's pi over 4 times the diameter of the cap squared minus the diameter of the rod squared. in order to get the solution for that. And you should easily be able to get a solution of about 21,900.5 PSI. Oh. I said it and then I wrote something else down. Would be the solution for that one. Next one. Okay, a little bit more to it. We're being asked for the pressure at that gauge. And there's different ways of doing this. I showed you last week a stepped method that may be more popular with a millwright, where we solved a pressure here. I'm going to call that P2 first. And then based on that, we could calculate the force here. I'm going to call that force 1. And then that allowed me to calculate this pressure here, which is what the question is really asking for. I'm going to call that P1. We could do that individually. Last week, I showed you a method where I used the area ratio. So after I'd found this P2, I calculated the area ratio and then just use that directly to calculate the force. The other thing is I could just add all my 3 equations together. Okay, so if I think about that at the very end, and this is what I tend to do as a mathematics guy, is I'm going to say, hey, listen, that P1, that equaled that F, that 1 that we calculated, and that area 1 at the cap side. Okay, that makes good sense. But what did that F1 really equal? Okay, that F1 equaled the pressure at 2 times the area of 1, because that's what's happening here on the annulus side, over that area of 1 on the cap side. But really that pressure 2, what did that equal? Okay, so that equaled, I can convert that into a force, which was force 2, over that area of 2 on the cap side. And then I still have the area 1 on the annulus side, area 1 on the cap side. And how do I calculate my areas? Well, if I expand this, my force 2 equals pi over 4 d1 on that cap side squared minus d1 the rod squared, all over, not all, okay, pi over 4 of what was that, area 2 d2 on the cap side squared multiplied by pi over 4, and that was that's d1 on the cap side squared. And why I like doing this is because I'm lazy. Well, that and other things. And pi over 4 cancels out. So it makes my math easier. It also eliminated a couple of opportunities for error. And that's a huge thing in design. If I can eliminate opportunities for error, okay, that's generally going to make a better design, a quicker design, a design that can easily be checked. So I end up with this equation, and then I fill in my numbers this way. Instead of doing them incidentally, though, calculating those 3 things, I calculate it all in one big equation. This is just algebra that you learned in high school in order to come up with an answer. I only wanted 2 decimal places, so make that a 3. And we're done. Okay, so 3 different methods of solving this. I covered 2 of them last week, the incidental one at a time, using the area ratio, which I think you need to use in either lab or 2 or 3 for one of the calculations, or doing it just as a great big mathematical situation. The 4th problem, size of a reservoir. Well, that's fairly simple. It's just a volume of a cubic rhombus, or whatever they call that, in order to be able to solve that. So the volume is the length times the depth times the width. Should be able to calculate that. Okay, and I want to convert it to gallons instead of cubic inches. Should be able to calculate that, and that would give me that was about 16 something gallons. Got it written down here, so I don't have to do the math and embarrass myself. Gallons. Okay. Time equals that volume of that reservoir divided by the flow rate of that pump. So what was that? We were given that here, 33.4 gallons per minute. When I divide that out, I'm going to get my answer of roughly 0.493. Okay, a gallon over a gallon cancels, and gallons per minute is equivalent to 1 over a minute. Put that on the other side. I get minutes for my units. So 0.493 minutes. Next question, what happens once the pump is energized? So initially, the circuit's turned off. The circuit's turned off, the flow rate equals 0. The speed that the cylinder is extending is going to equal 0. The pressure is going to equal 0. Force available, they're all going to equal 0. That's our starting condition. What happens? Well, we turn on the pump. Okay, we turn that pump on. So we start getting flow. Okay, flow. Oh, that's going to increase to whatever that pump is set to. Gallon per minute, 10 gallons a minute. So the pump's going to turn on, it's going to start rising. That's going to cause the cylinder to extend. So, you know, S is also going to increase, and that's dependent on the volume of that space, that cavity it's filling, and the flow rate delivered by the pump, but it's going to increase. Basically, the piston is going to extend. So as I go through these ideas, as conceptual ideas, what is happening in the circuit? Everything that's happening in this circuit. Because it's extending, okay, there's no real force there. It's not acting against anything. The force is still equal to 0. The force is equal to approximately 0. The pressure is equal to approximately 0. Now, there's going to be some friction, and there's going to be a little pressure as a result of it, but it's negligible in our systems. So what happens? The piston will fully extend and run into the deadhead situation. At that point, I'm still with the flow. Okay, it's still running at this constant value. The speed is going to now stop because, you know, the piston is stopped. It's acting against the end of the cylinder. It's deadheaded. So that means the force acting on it is going to increase until, and the pressure is going to increase until we reach the pressure setting of our pressure relief valve. Okay, so we get to static at the other end. That Q equals that constant value. The speed equals 0. The piston is stopped. Force equals a max. Pressure equals pressure relief valve setting. And that's what happens as that pump is energized. It goes through this series of steps from nothing to movement to the pressure relief valve kicking in. Okay. The sixth one, what is the head pressure PSI developed at sea level in the overhead stack reservoir? It's 5.2 feet above the intake of the pump. The specific gravity is 0.87. Okay, that's typical of hydraulic oil, lighter than water. So yeah, less than 1. Water is 62.4 pounds per cubic feet. Now we gave you an equation for this last week, and it's in the equation sheet and pops up in the labs, that we use an equation of the height in feet times 0.433 times specific gravity. That 0.433 is the density of water divided by a square foot, 144 square inches. And that'll actually give you 0.4333333 recurring forever. But millwrights don't like the idea of a little dot above a 3 indicating that 3 goes on forever. So we just simplify it to 3 sig figs often. But the most accurate answer is going to be this height in feet times this density of this water per cubic foot. Okay, over 1 square foot. Okay, well, those two will cancel out without 3, leaving just 1 foot there at the top. And times specific gravity. I've got a foot times a foot, which is going to give me a foot squared at the end for my units. I have to divide that by 144. Okay, 1 foot over 144 squared in order to get my answer, which is going to be, where did I write that down? I wrote that down somewhere. Which is going to be approximately 1.96 psi. And of course, I'm going to get a slightly different answer here than the actual answer, depending if I use this 0.433 or if I actually calculate that density. I'm going to get a slightly different answer at significant digits. Any questions for what was that, number 2? Breakout number 2. Nope. Excellent. Let's stop sharing. See people again. Any questions about your labs? I assume everyone handed their labs into Aman. I'll pick those up and mark those. Nope. Okay. So yes.
He said not to hand them in.
He said not to hand them in.
Yeah, he did.
Okay, I'll pick them all up next week then. Sorry, I was hoping to get them off him this week and mark them and get them back to you for lab. Okay, so I'll pick them all up off you next week. That means a heck of a lot of marking for me next week. That sucks. Not too keen on that, but it is what it is. And get those labs back to you. Oh, I didn't want that. I want to shut this down and have a quick look at D2L, which has expired because I've chatted for 2 hours. Quiz one is currently open and due. So I see a bunch of you have done that. There was a couple of errors. One was an odd error that took me a while to work out. If you think you've got a question wrong and you've done it right, let me know. 1, so I can give you the correct marks, and 2, I can fix some quick quiz questions that may be in error. So please do that. Oh, and I've lost my scrolling bar. I love D2L, but not very often. I want to go back to the main page. My scrolling bar is back. So quiz 1, get that done this week, please, and get that submitted. Remember, if you don't submit it, it won't submit. It doesn't magically submit when the time is up. And then next week, sequence and pressure reducing valves. We covered those today. In fact, the circuit you're going to build is very similar to what we covered today. And then we're going to do counterbalance valves the following week. So the next 2 labs are about the pressure reducing valves that we talked about this week. Next week, I'm going to talk about flow control. And then we'll start doing flow control in week 6. Week 7, we are on a break, reading week for that week. So for those of you not from Canada, the Monday is actually a public holiday. So you know, everything will be closed. It's a good week to take a break, a mental break. Studies in Europe have showed that taking a break after about 6 to 8 weeks is optimal for learning. And they've also shown it's optimal for instructors to take a break. Unfortunately, SAIT only does once in 1 semester, not the other semester. So the idea is to take a good break here. And, oh, quiz 2 is not up. I'm guessing that Stephen did not put that in. I'll have to fix that. Any questions? Nope. Okay, that's all I have for you this week. And I shall see you in person next week. My only symptom left is I don't have any taste, but that's not enough to keep me off campus apparently. So I shall see you back in the lab next week. Thank you very much.